in a very streamlined and interesting way using GitHub and GitHub Actions. And he's going to talk to us today about some tidy approaches to a certain type of genomic data analysis problem. Welcome, Jacques, and good luck to everyone.
Okay. Hi, everybody, and thank you for being here. Okay, and thanks to the Bioconductor team for organizing this conference. This is actually the first bioconference I'm attending to. I went to the Euro bioconference last year, which was great in Belgium, but this is my first time at the yearly Bioconductor conference. Okay, so I'm going to present this workshop that's entitled Applying Tidy Principles to Investigating Chromatin Composition and Architecture. And you should be able to reach this webpage by going to workshop.bioconductor.org, following the video that we have seen, and the workshop is available here on the left-hand side. So if you click here, you should have a Run Tool button that appears, and it should take a few seconds or minute to connect. And eventually you end up with this interactive window here, which in my case has already been started, and you should end up with this vignette here that has lots of unnecessary text for you, and conveniently, hopefully, there's also a link that I can provide. I don't know if I can provide it in. Is there a chat for this particular workshop session? Let me see.
We wanted to put it in a chat, was either the workshop Slack or.
Oh, I see.
Put it on the Ring Central. Which one is it?
Yeah, most likely the workshop. Okay, it's not necessary for the purpose of this workshop right now. Maybe I can put it later. All right. Okay. So essentially, this vignette shows you the same vignette that you should be browsing here, but in a prettier way with everything already executed. For those of you who are having a hard time following along the instructions. And please, at any point, interrupt me, ask questions. We're here to learn about how to do tidyomics and tidy analysis of genomic data. So feel free to interrupt, shout, and ask any question. Okay, so this vignette has been already filled out entirely, and I've generated another one that actually doesn't contain, has been stripped bare, only contains a handful of commands and some brief instructions, and I'll try and go along this vignette, fill out, do live coding, and then ideally we want to have interactions all together and see how far you guys can go in this workshop. Okay, so I don't have any slides. It's literally just going to be coding today. So before we get started, can anybody who has any idea of what tidy data analysis means, can they raise their hands? Yeah, a little bit. Okay, so for those of you who didn't raise your hand, tidy data analysis means essentially using a certain number of operative words, operative verbs to wrangle tabular data. And so probably some of you at least have used the tidyverse packages, a series of tidyverse packages, including dplyr, tibble, tidyr. And these different packages, they provide these operative verbs to manipulate standard tabular data, so namely data frames. In the Bioconductor ecosystem, we're facing a different challenge because our data is not tabular per se. it generally consists of some part of data frames, and in some other parts, genomic ranges and variates of genomic ranges. And there's also a core class of the Bioconductor, which probably most of you will have heard about, called Summarized Experiment, which is a super nice container that is designed to hold data and associated metadata all together. And so ideally, we want to leverage the tidyverse methodology to the genomic data that we have in the Bioconductor ecosystem. And to do that, it has been a extraordinary working group spearheaded by a couple of great people. And we altogether, so I think it's a team of 25 or 30 people. We have developed a series of packages, which actually you can find if you go to tidyomics. You have a list of the different, oh, here it is, yeah, all the different people. And the different repositories available through the tidyomics working group and project. And so among them, you see some called plyranges. Maybe some of you, anybody who has used plyranges already raise their hands? Yeah, okay, so some of you guys, okay. And then there are other packages such as plyinteractions and a number of other ones. So today we're going to talk about three different main packages. Plyranges, that is mostly used to manipulate genomic ranges as sort of tabular data. Plyinteractions, which is an extension of plyranges that is designed to manipulate genomic interactions, so essentially pairs of genomic ranges. And a third package that we're going to look over today is a recent package that I developed called tidyCoverage, that is, which aim is to extract coverage data from a series of genomic coverage tracks across a series of genomic ranges of interest. All right. Okay, so, and roughly the workshop is divided in, as you can see, three different sections. Maybe we can have a short break at some point during this workshop, but mostly speaking, we're going to spend a little bit of time on manipulating genomic range data, and then manipulating genomic interaction data through the plyinteractions package, and eventually manipulating coverage data through tidyCoverage. Okay, and so this vignette is divided in three main sections, and the first one is going to be focusing on plyranges. So typically, when someone wants to study genomic annotations, they would start by loading the genomic ranges package, potentially the R-track layer package, which can be used to import a series of different formats, genomic formats in R. And then they want to find their preferred bed file and then load it in R using the import function. And so to do that, I provided a series of example files. So if I look for this file, X, located in this folder, and the package that provide this file is the package that I wrote for this workshop. So if I do this, I should end up with, whoops, yeah. So this is the path to a bed file that I provided for this session. So I'm going to save that as a variable, bedf. And then typically, once we have the path to this bed file, what we want to do is just run the generic import function provided by R-track layer and BioCIO. And then that imports a genomic ranges of interest, genomic ranges object. And this one in this example contained 814 different genomic ranges, each one having a sequence name and ranges of interest and strand. Okay, so far so good. Hopefully this is all clear to everybody. Now the tidy way of manipulating genomic ranges isn't exactly following this, this method. it would be primarily to load this bed file as a tabular type of data. And to do that, we can use the functions provided by the tidyverse ecosystem. So I'm going to load the tidyverse package. Oops. Just bear with me. Yeah. Okay, so I've loaded the tidyverse, and now I have access to this read TSV function, which is essentially doing the same than import, but will coerce the bed file as a tabular data. And so when we load it, we end up with, again, a table. I need to, yeah. Okay. Yeah. Is that big enough? Well, then now. Okay. I don't have much space anymore to show the result of each command, but that's all right. Maybe I don't.
Low resolution.
Yeah. Okay. Yeah. So hopefully now it's better. Let me know if it's not. Maybe I can shrink that. I don't need. Okay, everything is taking place. Oh, I could. Yeah. Thank you. It's a little bit bigger. Okay. Right. So after loading this, I just need to specify that this bed file doesn't have column names. So read TSV is going to import my table as a data frame. And then the appropriate way using tidy version of coercing functions is to load the plyranges packages and coerce this data frame into a genomic ranges object using the as genomic ranges function. And so if I pipe this, so if I pipe this table into a genomic ranges, here it tells me I had an error message telling seq names column is required for genomic ranges. And so the appropriate way in this case is to specify which is the name of the seq names column. And in this case, it's x1. And then I can do the same for the start column, which is x2, and then n column, which is x3. By default, these are the names imported for a tabular file. And so we end up with this genomic ranges object, again, with 814 ranges. It's exactly the same than before. The difference is that we first imported the data as a tabular data and then coerced it in a genomic ranges object using as genomic G ranges function. So it essentially is the same way than importing, only it follows the natural process of tabular data. And I'm going to save this as, I guess, a bed object. Yeah.
How fast is read TSV?
Exactly. So that's a good point. So read TSV per se is not particularly fast. But because you can work with any package provided by the tidyverse package, you have alternatives that are purposely made to import files really fast. I'm thinking maybe about the vroom package or data.table package, which both can read tabular data really fast. And you can also customize which part of the file you want to import. So for really huge, massive bed files or any tabular file, I would recommend switching to any of these efficient packages. And then the as genomic ranges function, I don't have much experience in how fast it converts tabular data to genomic ranges, but I would expect the combination of these two to be at least similar to the import function in RTrack layer. But maybe they can correct me on that. Mm-hmm. Yeah.
So my question is, what is the, besides just like using tidyverse functions, what is the practical benefit of using this method of importing a bed file?
Right. So in this case, for the purpose of this example, there's no particular good reasons to preferentially use the tidyverse workflow style. But as I was mentioning, if you want to do prior filtering on your data, you will find that that would be exclusively based on tabular information rather than genomic ranges per se. You'll find the tables to be more efficient than genomic ranges. So yeah, if you have to do some filtering maybe on a numerical column, then it would be possibly faster to do that as a data frame rather than as a genomic ranges object.
I see. So the benefit is basically that you do the same thing, but you could insert additional sort of tidyverse steps in between.
Exactly. And then yeah, and then we'll see just now that actually once you coerce it as a genomic ranges object, you can still use the tidyverse operations to manipulate this genomic ranges object. So essentially, it doesn't make much difference. For the importing step, it just didn't follow the natural process of tidyverse workflow.
I guess another question I have is there anything similar to, because I think the vroom package, for example, doesn't actually import the entire file. It like does it lazily. Is there anything like that for plyranges, or does it just load in the whole thing?
So you're referring to delayed operations?
Yeah.
Yeah. So that's an interesting question. So I haven't tested it myself with genomic ranges. I would assume that if you do delayed operations on data frames, then you could pipe it to and coerce it as a genomic ranges object, and it would work seamlessly. I haven't tried it myself though, so it's a good point.
Yeah, I assume it would work, but would it force loading the entire file to create?
No, so you could use the vroom infrastructure to load specifically data by chunks, for instance, and then process that chunk, and then do your genomic ranges operations on that, and then go chunk by chunk on your massive bed file, for example, using delayed approaches. Yeah.
Okay, thank you.
Okay. Right. So now we have. Okay. Yes. So we have a bed file, which is a bed genomic ranges object, which is called bed. I think in the original vignette it's called GR for genomic ranges, but it's fine. And here we're going to see how to manipulate this bed file, this genomic ranges object, and following the tidyverse style of coding, I'm using the pipe and feeding any input to a endomorphic function. So in this case, I can add a new column to the bed genomic ranges object, and I'm going to call it maybe score, and I'm going to just to add some random numbers to it. Okay, so doing the mutate operations, added a new column called score with random values. And then I can also then do some filtering operation, for example, on this score column, saying I want to only get the genomic ranges that have a score higher than 0.2. And so now if I execute this, I end up with 634 genomic ranges. That number will change depending on what seed you have been using. And then maybe I can round my score just for the purpose of the example. I can say that I'm going to create a new column called round, and then that essentially is a round version of my scores. And then I can do a group by, this round column, and then I can do a summarize. Oops. Or, yeah. So, and for the summarization operation, I'm going to do the mean of the score column per round groups. And so the difference here, okay, so maybe I can execute just this bit here, which when we run these operations, we end up with a genomic ranges object with 645 ranges. Now it's a grouped genomic ranges object, so it's essentially behaving just like a grouped data frame from the tidyverse. And we have 9 groups coming from the round column. And so when I execute this and I add to this the summarize function, because summarizing over genomic ranges object, it wouldn't make sense to output any genomic range per se. So what we end up with now is a data frame from the Bioconductor version of the data frame with 9 rows and 2 columns. So each row corresponds to an individual group, and then the columns are the group values and the mean, which was calculated as the mean of the score. So if you have ever used tidyverse syntax and way of coding, that would look exactly like you would be manipulating a data frame, except the input is actually a genomic ranges object, and the output is not necessarily a standard data frame or a table. In this case, it's the Bioconductor data frame. Okay, yep.
So sort of a technical question. So here I suppose you have the S4, like G ranges is S4, and here
yes.
you have the S4 data frame. So have you ever gone to like a situations, like especially when you're like you like do like a dev tools load out when you're developing package. So do you often get into like nasty scenarios where because of the conflict between your functions here for S4 and the tidyverse's own like S3 methods with the same name?
Right. So these are mutate is an S3. It's a method that operates on S3 objects. But maybe I can add it here. If you look for, I think it's methods for mutate, you can see that the plyranges developers have created. So you have the standard mutate data frame, which comes from the dplyr package, and there are additional methods that have been defined in the plyranges package so they do not conflict with this method. Here we're using the generic function, but it dispatches to the correct class of objects. So it detects that the input is a grouped data frame, and it operates on it as such. Does that make sense?
Yeah.
Yeah.
So I had a related question. Bioconductor already has something that's kind of like a grouped G ranges, the G ranges list. Mm-hmm. How does that relate to using group by here on the G ranges?
Oh. I actually don't know. I wouldn't know. I don't know if any of the plyranges developers are around.
To have just functionality for converting back and forth between like group genomic ranges and G ranges list.
And G ranges list. Yeah, it's a fair point. So I actually don't know if that would work.
Try as.
MyCloud just posted that summarization won't work on G ranges.
Yes, the summarization, yes, but would can you coerce it as? No, it looks like you can't. It wouldn't work straightforwardly. So yeah, maybe room for improvements here.
Hey, so with regards to the final operation, when you summarize, what you end up getting is an S4 data frame, and I was playing with it, and you can't run any more tidy operations on that at that point forward. Yeah. Is there another package that does tidy for data frames, S4 data frames? Okay.
I guess that's one of the limitations, right? At this point, and I think that's a design choice to return that this summarized version applied to Bioconductor objects returns a Bioconductor flavor of data frames. The limitation is now if you want to, feed it to maybe ggplot, I think that returns an error. Oh, maybe not. Okay. So maybe it does work with data frames directly, the Bioconductor data frames. Yeah, but that's definitely something that we want that I would want at least to improve in the future is the conversions between Bioconductor data frames and other types of data frames.
So as chair, I'm going to just take the prerogative to ask whether you, I think this discussion is very good, but I know you want to get to chromatin conformation analyses. So if you
yeah,
sure
thanks. Yeah,
have time to do that.
It's fine if we don't, I think, but yeah, okay. Thank you. Okay, so another before we move on to the next ones is just to give an example of you can also, so when you have this genomic ranges object, I've shown how to add new columns, but you can also manipulate these sort of protected variables, so seq names and start and end and strand and width. You can modify any of these variables using the mutate function, and that will actually change. So now if I say seq names is 2, whoops. Oh, okay, so that's a bad example. So here it tells you that you cannot change the seq names because the sequence levels that are recorded in this bed are only 1, I think. Ooh. Okay, I'm not sure. I need to put that as a factor. Factor of 1, and the levels, oops, would be the levels of, well, the sec levels of bed. Yes, okay, now that works. So if I put 2, is that gonna work? Yeah, so I can change dynamically this sequence names, still using the pipe version, and then I can also play around with maybe, whoops, the mutate of the start, and I'm going to put everything at, for some silly reason, 10, and then, so we can see that the start was affected, and then I can also mutate, maybe the width is going to be 100. And so now, oh, it's not W, it's width. Okay, so now everything is, all the ranges are sequence name of 2 and then 10 to 109. But you could play around with these values and put actual sensible, meaningful variables here. Okay, and then I'll let you guys go through the more advanced manipulations of genomic ranges using the advanced plyranges functions that could be used to anchor genomic ranges at either the start, the end, or the center. And you can also resize using stretch and shift and flank, which are essentially wrapping functions for the already existing functions provided by Bioconductor genomic ranges and iRanges. Okay, all right. So moving on to manipulating genomic interaction data. So before we move on, is there any question regarding playing genomic ranges objects? No? We're all good? All clear? Awesome. Okay, so moving on to G interactions. Can anybody who has used G interactions objects raise their hands? Yeah, I see one. Great. So G interactions stand for genomic interactions. It's an extension of genomic ranges objects, and it is defined by the interaction set package. And essentially, if you conceptually, if you consider a genomic interactions, it is defined as a pair of genomic interaction each side of genomic ranges, each side of the pair is referred to as an anchor. So you have anchor 1 and anchor 2, and the pair of these two is a genomic interaction. Okay, so if we load the interaction set package, we should have access to a number of, a number of different functions from there. And the one that we're going to look through to begin with is the G interactions function. So this this creator function can build genomic interactions, and you have you could specify maybe genomic ranges of 1 going from 1 to 10, and then and then a second genomic ranges of maybe 2 going from 20 to 200. And if you execute this, it will create, there's a typo here. So you can actually coerce these genomic ranges from strings, and it will create, so this is a genomic ranges with a single range. And so I have the anchor 1s here and anchor 2s here. And so if I wrap all of that into a genomic interaction, now I have a genomic interaction object with one single interaction. And this side G of the genomic interaction before the 3 dashes indicates the anchor 1, and all of this indicates coordinates for anchor 2. Okay, so if we were to actually, maybe I can do that. So I can create, I'll do 1 and 30 to, 40 to 400. And then I'll create a second one. So here I'm just going to create a genomic interaction object with 2 entries just to highlight how this goes. And to also emphasize, so now I have fed 2 genomic ranges as anchor 1 and 2 genomic ranges as anchor 2. And so they end up stitched together. So I have now this one that goes with this one. And so we can see that this is an interaction with itself. So it's a genomic interaction to a set of coordinates to the same set of coordinates. And we can also have genomic interactions that connect segments of different chromosomes. So in this case, it's chromosome 1 and chromosome 2, some part of chromosome 1 and some part of chromosome 2 that are linked together as a genomic interaction. And that conceptually has meaningful implications, because if you consider genomic organization, you can actually have physical connection between different chromosomes. But for now, we'll stay at the level of the data representation. Okay, so that's one way to create a genomic interaction object. Another way is to actually define a number of regions, and the regions represents the pool of available coordinates to build genomic interactions. So here I'm going to say, 1 from 10, from 1 to 10, and then, I'm just going to make a bunch of these regions. Oh. Did I mess up? Okay. I don't know if that changed the... Yeah, am I the only one who's having trouble? Yeah, okay, I probably pressed the wrong key.
You should go back to the view before, so you don't show your
Sorry, yeah? Oh, good. And it looks like the libraries are still there, so. Genomic interactions, so I was here manipulating genomic interaction data. What are genomic interactions? Okay. So does that, yeah, that still works. Okay, so I was here, and I'm going to be more careful with this. Okay, 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 5 is going to be enough. And then from 11 to 20, and then 21, 31, 41 to 50, 40. So here I'm creating a number of different regions. And these regions, they are a plain genomic ranges object. And now what I can do is combine these genomic interactions, these genomic ranges into genomic interactions, saying that my regions is provided here. And I can say I want to actually link the anchor ones, which are going to be specified here, maybe 1, 2, and 3, to, whoops, the anchors 2, which I'm going to specify as 2, 4, and 5. Okay, and so here, what this does is, instead of actually giving individual genomic ranges, I'm giving indices of the regions to use as anchor 1 and indices of the regions to use as anchor 2. And so the result is here, now I have 3 interactions. And this is, when it comes to programming and analyzing genomic interaction data, this becomes a lot easier to use than the previous constructor that uses 2 sets of genomic ranges separate. Okay. So this genomic interaction object now has 3 interactions, and we'll see now how to play with a real-world example. Oh, yeah, there's a question?
Yeah, quick question. Are these interactions directional? Does it represent, like,
yes, they are.
The left and center? Okay.
Yes, they are. They are, and so you'll notice that every time I tend to have the upstream interaction on the left hand and then downstream interaction on the, or anchor on the right hand. But you can actually have, here if I replace 4, now I have on the left hand interaction going from 31 to 40 back to 11 to 20. So it is oriented as in this is anchor 1 and this is anchor 2. Now if you do, I believe, is it sort? Yeah, if you run that to sort, it swap the anchors so that the anchor 1 is always upstream of the anchor 2. So it's sort of
is that sorting the rows, or it's flipping anchor 1 and anchor 2?
Here,
or both?
I think it does both. So it swaps the anchors so that anchor 1 is upstream of anchor 2, and then it also reorder the rows to have them ordered by anchor 1 and then anchor 2.
So that means that, practically speaking, it treats anchor 1 and anchor 2 as interchangeable.
So they are, it means something if you have a genomic interaction in genomic range in anchor 1 or anchor 2. That's an information that you may want to retain. But then you can manipulate.
In that case, you wouldn't want to call sort on that if it has a meaning.
Exactly. Yeah, I can either keep it as it is, like this, or add a sort if I want to make sure that they follow the canonical orientation of a pairs provided in other files.
Okay, thank you.
Yeah. So canonically, it's always preferred to have the left-hand side as upstream and the right-hand side of downstream. There's not a requirement. Okay. All right, so find a bed PE file. So to showcase a real example, I've provided a bed PE for bed paired end file somewhere in this package. So I just need to find the path again. So the name of the bed PE is, so I'm going to find it in Xdata, and the name of the bed PE file is S288C loops. And so this bed PE file actually contains physical chromatin interactions identified in yeast in this genome reference of yeast genome. And so the package is that unnecessarily long package. And so if I do so, I find the location of this bed.pe file, which I'm going to copy and save it as a variable, okay? And again, I think we could import bed.pe file with our track layer. Oh. Sorry? Okay, so it doesn't, oops, format. I need that. It doesn't seem to know about the, oh, yeah, sorry about that. Yeah, okay. Right. Okay, so there is an import method for bed.pe files, which import this bed paired end as a pairs object. So again, pairs data objects, I think they're provided by Bioconductor as well, but they're not exactly what the genomic interactions are, but they're nearly what a genomic interaction is. So the more tidy style of doing this is again to import the bed.pe file as a TSV. And so now we end up, again, with the call names. So now we end up with a table that has 162 rows and 6 columns. And these 6 columns are chromosome, anchor 1 chromosome, anchor 1 start, anchor 1 end, and then anchor 2 chromosome, anchor 2 start, and anchor 2 end. And so I actually need to specify that when coercing into the as G interactions, and then I have to say seqnames 1, just like I did if I scroll up for, where is it going to be? Whoop. Here, just like I did to specifying seqnames start and end. Now I have to do it, but for both anchor 1 and anchor 2. So I was here, right. So I'm actually going to copy and paste and then add 1, start 1 and end 1. And so now these columns indicate data for anchor 1, and then seqname 2, start 2, and end 2 indicate the location for anchor 2 columns. And hopefully that, whoops. Oh, and it tells me find the as genomic interaction function is not found. And that's probably because I need to load the plyinteractions package. The plyinteractions package is the equivalent of the plyranges package. Plyranges operates on genomic interactions, and interactions operate on genomic interactions.
Excuse me, a quick follow-up on my previous question. It looks like I was testing out the sort in my workshop, and I think it only sorts the rows. I don't think it will flip the thing, the anchor 1 and anchor 2. So 21 to so this one here, this one. So it sorts by the anchor 1 and then by anchor 2.
Oh, I see. But
anchor 2 is in front of anchor 1. It won't flip them. Okay,
so I thought it would do, but you can. I thought that the sort function included this swap anchors, which is provided by, as well by the interaction set package, and that swap anchors does the operation of swapping the.
Is that an unconditional swap, or does it swap them all so that they're in a certain order?
So it's a good question. Okay, so there's a whole set of functions or methods provided by interaction set, and if you look for, there's a mode indicating what type of swapping should be performed, and you can either swap both as a whole, or swap them so that is the upstream is left hand and the downstream is right hand.
Okay.
Yeah.
Just wanted to correct that since we just talked about it earlier.
Good questions, yeah. Okay. Yeah, and so you could either pipe that to sort if you want to really be sure that it's already sorted, but in this case, I think it was. Okay. All right, so I've specified there's 6 different required columns because you need all of these information to build a genomic interactions object. And now we end up with genomic interactions that has 162 entries, 6 columns. And so this is actually the parsing the bed PE file as TSV. This is the output of the read_TSV function, and then the output of the as genomic interactions is here. Maybe I can just create that GE object for genomic interactions, and then print GE. Okay. So this is my genomic interactions object, and it tells me that I have 316 individual regions that make up 162 interactions. So there's a little bit of redundancy, I guess. Maybe not, 162 times. Yeah, there's a little bit of redundancy. So some regions are used in multiple interactions, which can happen. Okay. All right, so now manipulating genomic interactions the tidy way. Again, it's essentially an extension of plyranges. So all the operations that would work on genomic ranges have been, as much as possible, adapted to genomic interactions. So if you want to change different columns, you could do as such. So we have our genomic interactions, and we can mutate, just like we would mutate a different column, we can add score of runif. Okay, so we've added an extra column here called score. And again, I could filter this column on this column using maybe that. And so I end up with now 131 interactions in my case. But I could also manipulate these seq names 1 and seq names 2 or ranges for start1 and start2, for example. So start1, maybe I'm going to say is going to be, actually I'm going to do start2 is end1, just to show you, oops, I forgot to mutate. How this works. So now I've specified that the start2 column should be equal to end1. And so you can notice that now every start value in this ranges 2 here is the same as the end1 value. So the end for ranges 1. And so that's one way to mutate columns. You can also do maybe strand 1 is a plus and strand 2 is a minus. And so you can orientate your, now each genomic ranges that build a genomic interaction can be stranded, and you have a plus here and a minus here. So the interactions go facing, so yeah, the anchors of each interaction are facing each other. If that makes sense. And one thing that we typically are concerned with when we work with genomic interactions is to know whether the genomic interactions happen in cis or in trans. And so cis and trans here refer to whether both anchors of a single genomic interaction entry are located on the same chromosome or are not. And so I can create this is cis column, and I'm going to query whether seq names 2 equals seq names 1. And so now I have a certain number of, well, here it looks like most of them are true. Maybe they're all true, actually. That indicates that indeed seq names 2 is equal to seq names 1. Okay, so we've just seen how to filter interaction using the filter verb. Let's see what comes after. Okay, all right. So filter and mutate, we have used that. So they work virtually the same way then for tidyverse and or plyranges. You only have to adapt the variable names that you change or filter on. And so one thing that we also typically have to do is do some overlapping operations. And just like you could overlap genomic ranges with other genomic ranges of interest using plyranges functions, namely the join overlap left function. You can use it to overlap a set of genomic interactions with a set of genomic ranges of interest. And in here, well, I didn't finish my sentence to work with interactions. So here I provided another file, which I'm going to call centro-f, and it's system file. It's also provided by this package, .txt, and package is 24 tidy workshop. Hopefully I haven't, whoops. Hopefully there's no typo here. There is. I got that wrong. Like 2024 workshop. Okay, so now it seems to have worked. So this is the location of this file, and so we can see that it's not provided as a bed file, and this is a good example of why it can be relevant to use tidyverse importing functions first to manipulate the data. So we'll have a peek at this file using read TSV of this centro-f. And here we can actually see that now this file here contains column names, so we specify that it doesn't, and it has a number of relevant information. So sec ID, which isn't called chromosome CHR or seq names, but that's the equivalent. There's also start and end, but we have in strand, and we have an additional pattern name. Is there any question online or? No, it's just some people talking. Yeah, okay. All right. And so we're going to, again, apply the plyranges as granges function provided by plyranges. And we just have to specify that the seq names column is should be retrieved from the sec ID column here. And so now we end up with a genomic ranges object. And there are 16 ranges. Each one specifies the location of an individual centromere over the 16 chromosomes in yeast. And I'm going to do 2 extra operation on this. Whoops. Genomic ranges. I'm going to anchor it at the center, and I'm going to then stretch it to 20 kb. Ooh, let's see. I think it's that one brown key that I hit. Does that still work? Yes. Okay, so so anchor, center, and stretch. These are strictly equivalent to resize, and you could say fix at the center and width of 20 kb. So actually this here is the same than this anchor, center, and stretch, but this is provided by the standard genomic ranges and iRanges for the standard iRanges object, whereas this can is provided by plyranges. Okay. So that's our centromeres, which we're going to save as centro object, okay? And now what we can do is filter, we can use our genomic interaction object, and we can say join overlap left. So it's the equivalent of the dplyr left join, if you wish. And we're going to join it to overlap with centromeres. And let's see how this looks. So now what we have is added columns, pattern name and pattern, that have been taken from the central genomic ranges and have been added to the genomic interaction, the original genomic interaction. And we can see that from most of the entries, there's NA because it doesn't, genomic interactions do not overlap with any genomic ranges provided in the centro. There's only a few of the interaction pairs that overlap with centromere annotations and recover pattern name and pattern. So what we can do then is, if we want to, is to filter, and we want to only retrieve those that do not have an NA value in the pattern. And we can see that we have 5 interactions overlapping, genomic interactions that are overlapping centromeric annotations in this data set. Okay. Is there any question at this point? No? All good? And so here I've exemplified the join overlap left function applied to a genomic interaction object, but bear in mind that it's a method that has been, whose generic has been created in the plyranges package, and it would work with another genomic ranges instead of a genomic interaction object. Okay. All right. And then so here, maybe a question that could arise is when you perform the join overlap, does this join query, does this join operation queries the anchor 1, so the left-hand side, or anchor 2, so the right-hand side of genomic interactions? And by default, the join overlap left, so the left refers to just the fact that it takes this genomic interactions. It doesn't refer to the left-hand side of the genomic interactions. Nomenclature is a bit complicated. But one way to indicate which side of the genomic interactions you want to use when you query for overlap with specific genomic ranges of interest is to first pin your anchors. So if I do pin anchor 1, anchor 1. So this doesn't do much. This only wraps the genomic interactions into a pinned genomic interactions object, indicating that it's pinned on anchor 1. So for now, we haven't changed anything to the data, except we've added this information that is pinned on anchor 1. And so when we do the full operation with the join overlap left centros, oh, sorry about that. I need to add a pipe. Okay, so now we see that there's only a single interaction that is retained here when we pin the anchors 1. So when we specifically ask for an overlap between anchor 1 of the genomic interactions and the centromeres. If we were to do that with anchor 2, now we have 4 overlaps. And a total of these 4 overlaps plus the 1 overlap from the anchor 1 equates an overlap of 5s. So you can see that the join overlap left by default, if you don't specify any, if you don't pin your genomic interactions to either anchor 1 or anchor 2, you do the overlap with any of the 2 anchors. Yeah.
And so it overlaps with anchors. What if it's inside the region of the anchors? Yeah.
So with in between the anchors, right? Yeah, that's a scenario that you may want to recover. In that case, there's no dedicated method that would work within this pipe workflow. What I would recommend then is to create a genomic ranges object that spans from start 1 to end 2, so it creates a whole. But then it's a genomic ranges. It doesn't. You lose the genomic interactions nature. Yep.
I also have another question. Like, if I have two genome interaction objects, is there a way to manipulate them, like find an overlapped interaction pair, like overlap loops, like in this case?
Yeah. Yes. So not within the plyinteractions infrastructure, because it becomes really complicated to wrap your head around. What am I overlapping? And for each of these, if you're overlapping interactions versus interactions, then that becomes a tricky situation. But you can do that using the standard subset by overlap. So subset by overlaps now has a method for genomic interactions. So genomic interactions versus genomic interactions. But the standard one used by join overlaps left is for genomic interactions versus genomic ranges natively. Yeah.
Thank you.
So, quick question. So
Yep.
you have these G interactions. So like for real biological data, it could be very interesting. So do you have like a plotting function for to plot this?
A plot function?
Yeah.
Right. Yes, I do. It goes beyond the purpose of this workshop, I think. But there's it's another package that I wrote specifically for chromosome conformation capture data. It's called high contacts, and it can plot genomic interactions as a matrix. So what you'd typically see in high C or micro C papers.
All right, cool.
Yeah.
Thanks.
Okay, good questions. Yeah. All right. So filtering here. And here's about a real world use case to compute what we typically refer to as a P of S, which is the probability of, or the interaction frequency as a function of a genomic distance, separating the two anchors of an interaction. And so what we typically start with to generate this P of S, or distance law, it's sometimes referred as, is to import data from pairs files. So this pairs file is something that probably most of you have not encountered yet. It's a flavor of BedPE, but it has a certain order of the columns and has also additional required columns. And so I've provided an example, and they're typically huge because they're direct representation. So it's essentially just like a BAM file, but for pairs. So I provided a tiny subset of pairs taken from mouse embryonic stem cells using chromatin conformation capture, and you can find it again using, and the package is here. Okay, so it finds this file here, which I'm going to name, pairs F. Okay, and I'm going to read it as a TSV again. And this is, I would say that this is a good example where you want to, maybe run this through a tidyverse flavor of workflow and analysis, because these pairs files can build up to several gigabytes, and sometimes like 20 gigabytes compressed. So they can be really huge data sets. In this case, what do I have? I have 1 million. So I've subsetted 1 million, which is already quite a decent amount of data, but it's really not much compared to what we can end up manipulating as output of chromatin conformation capture. And we can see that it has, so 1,032 rows, and the extra 32 rows come from this header information that indicates the chromosome size. So these are a requirement of the pairs data structure. And there's additional columns. Can I see them? Oh, actually, sorry, no, here there's just one column because I need to specify that I do not want these comments to be imported. Right, so I'll say call names is false, and I'll specify my comment is hash. So again, takes a bit of time to parse. Bear in mind that this is 1 million interactions. Oh, sorry, a little bit less than 1 million interactions for some reason. And I now have 7 columns. So we can see again that it has chromosome 1 and just a single coordinate, and chromosome 2 and a single coordinate. And that's how the pairs, one flavor of the pairs file is, it only includes a single coordinate indicating the position of interaction between, so between this location and this location, and you have strand 1 and strand 2 for of anchor 1 and anchor 2. And this is information for the read ID or whatever. So what we can do is then chorus it as, we're going to chorus it as genomic interactions directly. And we have to specify again, seq names 1 is x2, seq names 2 is x4, and then start 1 is x3, and start 2 is x5. Oh, yeah, thank you. Yeah. And then I can also specify that strand 1 is in x6 and strand 2 in x7. And I'll also say that I want to keep extra columns just to retain this x1 column here, just for the sake of this example. I'm going to save that as a GI object. Okay, and it failed. And it fails because it asks to provide either and or with information, because by default, genomic interactions, each anchor of a genomic interaction is defined by an interval range spanning from start to an end at a specific width. So one way to alleviate that is to say, I want my end 1 to be also x3, and my end 2 to be x5. So now I have just positions, and we'll see how this looks. Oh yeah, thanks. Yeah. Well, the error actually said named argument can only be, there's a space missing here, but I have to, yeah. So that was a typo. All right. Okay, and we now have a genomic interactions object with about 1 million interactions, different strands, so oriented. Again, you can see that I think by default, the pairs files have to be ordered so that the anchor 1 is upstream of the anchor 2. And we've kept the extra column called x1. Okay, so that's our...
I have a quick question about the data representation here.
Mm-hmm.
So the x1 column over there, that's metadata on the entire G interactions object, right?
That's the read information coming from, so it's information that is contained in the pairs file, and that indicates which fragment of the flow chip.
So my question is, does the G interactions object actually contain 2 G ranges objects inside of it? And do those also have their own metadata that's not shown here?
Yeah, very good question. So how to answer that correctly? So it has all of the situations. So if you look for the regions of the GI, the regions is a single genomic ranges object. that has 1,000,000.9 entries in it. And these don't have particular metadata, but they could have. So I could say regions G1, and I'll say
score equals 5, whatever.
Well, I'll say whoops. I'll store it as a SN, and then I'll store the seq name just because it's going to be easier to see.
Mm-hmm.
Okay, so okay, and so now if I type again regions of GI, whoops. Now I have an extra column which contains the information for seq names. Now if I print my GI object again, it hasn't changed. So it doesn't, this SN column doesn't appear here. What is possible though is if I do anchor of GI anchor 1, now I recover this SN.
Okay, so there's one GRanges object that has all of the anchors for both sides.
Exactly, and that's the regions.
And it could have its own internal metadata that is not shown when you just print out the G interactions.
So it doesn't show up as metadata for the G interactions object, but it is stored in the anchors slot of these G interactions.
Thank you.
Yeah. And you could also, so if I were to say GI SNSN, for example, would be paste seq names 1 of GI. This is not very tidy style, but just for the purpose of here, and in GI. So now I have metadata specifically for the pairs of interactions, SNSN, which do not exist in the, in the region because they only concern pairs of interactions. So that's something that, yeah, you have to keep in mind. It's a good point. Okay, so a typical example that we have to do when we end up with these pairs files is to count the occurrence of interaction separated by a genomic distance of interest and specifically by the orientation of each strand. So one way to do this is to say, okay, I have my GI and I want to quickly add the pair dist or the pair distance, which is, whoops. Oh, I see now. I'm just going to remove this GI SNSN because it takes away the. Okay, it's easier to read here. Okay, so pair dist is a new column that is added by this function. It's essentially calculating the difference between start 1 or end 1 and start 2 actually. So the inner distance between interactions, separating two different interactions. And we can see that it has different values. And just for the purpose of this example, I could say I want to filter this pair dist to be lower than maybe, let's say 2 KB. And then I want to maybe group by strand 1, strand 2, and pair dist. And so if I do that, I end up with a grouped genomic interactions that has this many groups. And each group is a combination of strand 1, strand 2, and this pair dist variable. So I guess if I were to, I'm not actually sure how that behaves. Maybe that. Yeah, I don't think that the sort, I don't think I ported the sort function to grouped genomic interactions. Okay, let's forget about that. Okay, and so we have these grouped genomic interactions, just like we've seen grouped genomic ranges. And what we can do is now apply a count function, which is well, essentially a summarize n equal is sum of n. And so you end up with, again, a bioconductor flavor of data frames with the same number of rows that were there were groups in the grouped genomic interactions. And so there's an added column called n indicating how many entries there are per group. for strand 1, strand 2, and pair-dist combinations. And so I'm just going to save this in a data frame, a DF object. And then from here, I can actually plot this. And I'm just going to print to show what and here I'm going to print this data frame using the pair-dist variable as x, and in y I'll put the n, and I will color using a combination of interaction of strand 1 and strand 2. And I'm going to use the smooth just to make it simple. And I'm going to scale that y-axis to a log version. Okay, so here the plot is generating. Geom smooth can take a bit of time to, yeah. Takes a lot of time to run. Shouldn't take that long. Okay. You had to refresh too as well? Or it's still. Oh, okay. Well, the data frame is just 7,000 rows, so I'm surprised that it takes so much time. Maybe it's running. It's getting hard on the environment. No, 1.8 gig. Okay. Anyway, so we have the breakdown of these interaction frequency here, or actual number of interactions. So here on the x is the distance, the genomic distance separating two anchors, and in the y-axis is the number of interactions in our original file. And we've used a smooth version of the data representation. And so we have 4 different curves. 2 of them are really overlapping closely. It's the strand combination of minus and plus, meaning that these come from interactions for which both anchors are oriented in the same direction, so either facing so plus or minus. And we can see that there's an enormous enrichment of interactions that are plus minus at short distances. And this has to do, comes from some artifact. When you perform chromatin conformation capture, you end up with a lot of religation when you do the experimental part of the process, and so you end up with these plus minus interactions being enriched at very small genomic distances. So essentially, you'd have to say people tend to consider that anything that goes away of this minus and plus in this plus minus distribution here, anything from here and closer genomic distances would be artifactual. Okay, so this is a typical diagnosis plot that we'd have to generate when we do chromatin conformation capture, and that indicates us whether the experiment has been somewhat successful. And in this case, it seems to be high quality. And then, yeah, I think I have a couple of minutes to wrap this and plot P of S. So the P of S, again, stands for, is a way to call the genomic distance-dependent interaction frequency. I'm generating these bin width and bin breaks because they're complicated to, I can never remember how to generate them, but they're log-spaced bins. So they're each break is growing a little bit. So you have breaks that are spaced of 1, and then at some point spaced of 2, and then eventually spaced of a lot more than 2. So it's a good way to represent growing data with growing distances. Okay, and so one way to use these objects together with our, whoops, let me just go back here. Okay, can that work? Yeah. So now if I take my pairs, again, I add my paradist. We've done that already. And I would typically name it as S, and that's the S that is referred to in the P of S here, probability of S. So S stands for genomic distance. Oh, and tells me, oh, it's GI, sorry, it's not pairs. Okay, so again, same column created, only I renamed it S. And then I'm going to mutate these to say bind S is bins breaks. And we'll see in 1 second what this does. It is actually quite complicated operation, but hopefully you guys bear with me. And so what this does is it assigns specific genomic distance bins to any of the genomic distance S. So now I have a rounded version of this S distance. And we'll see in a minute why this is relevant. So there's another column named bin width. Whoops. I have my cheat sheet just besides, so I don't remember how to type these by heart, but there's maybe other ways to do it in a more straightforward way. Okay, do I have to put a pipe here, I guess? Yeah. Okay, and then I'm going to group by bin S and bin widths. Okay. So I've added 2 extra columns specifying a bin version of the genomic distance and the corresponding bin width. And now I've grouped according to these 2 variables, so bin S and bin width, and I have 175 groups. And so what I can do is to count these, the number of occurrence for each of interactions in each of these groups, and right. And so when I run this, I end up with a data frame with 175 rows and 3 columns. So it looks just like what we've done in the previous example, only here I haven't grouped by the strands, but by binned distances and bin widths. Okay, and so here you would be, you'd need to do a further operation to say that you want to, in order to normalize the number of interactions by the bin width, you could say, I want to normalize my P of S is n divided by the sum of n divided by the bin width. Whoops. And this is a way to normalize by sequencing depth and the bin width for each bin. And so if you run this, it actually isn't going to work. For a reason that we've raised before is that the mutate function cannot work on bioconductor flavors of data frames. And that's one of the limitations of returning bioconductor data frames from this count, that you have to, in order to do this, you have to specifically convert it to a standard data frame or table version. Okay, and so we end up with this table, and it has a column called P of S, and that represents that probability. And so if I save it into DF maybe, I'm going to then plot this DF. Just going to show how it's structured. And so I'll plot as X, I'll plot the binned S or the bin distance, and as y, I'll plot the normalized probability of interaction. And I'll represent the data as a line. And again, just for representation purposes, I'll scale the axis to log axis, and that's pretty much it. Okay, and so I end up with here a plot with, on the x axis, this genomic distance separating two anchors, and here the probability of interactions occurring at each of these genomic distances. And so we can see that below 1 kb, which would be somewhere here, actually, we can see that there's a giant enrichment which we have discussed just before, which is artifactual. But after this 1 kb critical point, we end up with a smooth distribution of interaction frequencies with a decay along the increasing genomic distances, which is expected because you have decreasing physical interactions in the DNA, in the chromatin polymer, as the genomic distance increases. Okay, and again, that's more than a diagnostic plot. Actually, that's typically some of the endpoint analysis when you perform chromatin conformation capture. The behavior of genomic interactions as a function of the genomic distance is typically something that we'd want to measure, and is typically one of the purposes of performing chromatin conformation capture. Okay. Any question at this point? No. All right.
Well, you're right on time, and I'm told that there are no online questions.
Okay.
There were some about links, but those were all resolved. Last chance for questions or comments?
Maybe I can just give a quick word on the third section that we actually haven't covered, but it's all good. It's to manipulate coverage data. And in 30 seconds, I would have wanted, but couldn't have time, to introduce you to the tidyCoverage package, which you can install from Bioconductor, and it defines these two additional classes, coverage experiment and aggregated coverage class of objects, which behave sort of similar way to summarized experiment classes of objects, and that are typically used to, actually maybe I can find it in here in the field out, and then you guys can go through the section yourself. But essentially, you can pass a series of tracks and a series of genomic features of interest, so provided as bigwig file and genomic ranges, and build a coverage experiment object on these, and this function will create a summarized experiment flavor containing the coverage signal for each of these tracks over each of these feature sets. And you can manipulate it using the tidyCoverage package and tidy's summarized experiment package. I'll stop here. There's a link, I think, in the Vignet to the tidyCoverage manual. So you're welcome to browse it and ask me questions if you want. And that'll be all. Thanks.
I guess I will just query quickly on visualization in the context of a genomic browser. Have you looked at JBrowsR? Is that functional with these sorts of things?
Right. So I think these are separate projects. The tidyCoverage does provide a way to visualize a collection of tracks along individual genomic loci, which would be the equivalent of GBrowsR, but in a non-interactive way. So I would still rather use GBrowsR for that, or even just plain IGV. But the original purpose of tidyCoverage is really to aggregate the data and generate these aggregated plots that we know. Maybe I do have one here. Actually, if I go to tidyCoverage, maybe there's an example in the vignette. I can't type anymore. Whoops. Right, yes. So it's the purpose of tidyCoverage is to make these aggregated plots over, for in this case, for example, the transcription start sites showing the enrichment of POL2 and MNA's signal. So it goes a little bit beyond the gbrowse-R purpose. So it's the equivalent of deep tools in Python for those of you who've used it, but in R. So yeah. All right.
I'll close the session. Thank you again, Jack.
Thank you, everybody.